In the video, the large cube was broken up into 27 smaller cubes. So we have the one large cube. The surface area was 9 centimeters for each square, and then there's 6 of them. So the total surface area is 54 centimeters squared. The volume is 27 centimeters cubed. So the surface area to volume ratio, if we take a look at the ratio of these two numbers, if I simplify this ratio, it becomes a 2-to-1 ratio. So when I do this with the smaller cubes, I have 27, each cube is 6 centimeters squared, the surface area, because the 1 by 1, and there's 6 sides. And there's 27 individual cubes now, so there's 162 centimeters squared of surface. The volume remains the same, so our surface area to volume ratio is 162 to 27. So when we divide that, 162 divided by 27, we end up with 6. So we end up with a 6-to-1 surface area to volume ratio. So by just looking at the numbers, when we have smaller pieces of the same shape, okay, same volume, but we broke it up into smaller pieces, we have much greater surface area to volume ratio. So there's a lot more surface area over here for the individual cubes than for the one big cube. So if we had one giant sugar cube, a 3 by 3 by 3 centimeter cube, and a whole bunch of smaller 1 centimeter cubes, which would dissolve faster in water? Okay, so the smaller cubes would dissolve much quicker in the water. Okay, so the smaller cubes would dissolve much quicker. And what's the reason? Okay, the reason why is because there is much greater surface area contacting the water that allows the molecules to come apart and dissolve into the water. So there's much greater surface area for the same volume of sugar. Okay, so that would be an example of where surface area, the increased surface area for the same amount of sugar, would change the dynamics. So that changes the solubility, or how fast molecules would dissolve in the water. So I want you to kind of think of where does surface area, as we change the amount of surface, that it affects some sort of process. For example, would be, and come up with a different one, if you have a wet t-shirt all scrunched up in a ball, sitting in the corner of your room, or if you took that same wet t-shirt and flattened it out and hung it up on a hanger or on a clothes rack, which one's going to dry quicker? Okay, obviously the one that you flattened out and you hang, because when you do that, you increase the amount of surface area for that same volume, and that allows the air to interact with the water molecules and pull the water molecules off of the shirt and evaporate. Okay, so that would be another example. So I'll give you one more example here, and when we talk about heat transfer. Okay, so if we take where you would have greater heat transfer is if you could have lots of surface for the heat transfer to occur. So an elephant, if you take a look at an elephant, the elephant's ears are very, very large relative to its body. Okay? It's because it needs to be able to, the elephants live in a hot environment, so they need to sometimes cool themselves or lose heat out of their ears. So the large surface area of elephant's ears allow for a greater amount of heat transfer. Okay, so that would just be one example. So try to think of something that you've seen that may affect, things like heat transfer, evaporation, okay, solubility when you try to dissolve things in water. Okay, these kind of things are affected by surface area. Okay, and when we have chemical reactions, the amount of surface that interacts with the molecules allows for faster chemical reactions as well. So the surface area will affect the rate of chemical reactions. So let me just finish this here. Large surface area of elephant ears allows for a greater amount of heat transfer. Okay, so this would be just one example. You can come up with many examples of this, but try to think of one and write it down.